Welcome to module 10. In this module, we will go over some of the calculations using the process network algebra that we learnt in the last module. In last module, we considered simple system where we had only one product. We will also in this module go through some of the systems when we have multiple co-products from the same process and see how do we modify the process network algebra to accommodate for multiple products. So, to start with, we will go over the same system that we looked in the last module and do a simple calculation. So, here we have the modules where first process is giving fuel, which is the fuel production process, and we have electricity production. Of course, the fuel that is being produced by process 1 is also an input to the process 2, but it might also be going as a product to the economy. So, the goal of our LCA, in which we only have our two systems included, which is the scope, is to calculate the life cycle environmental impact of producing 500 kilowatt hour of electricity. So, when you have this problem, the first thing we will do is to develop the technology matrix and the intervention matrix and then set the final demand. So, in this network we have two products, fuel and electricity. So, your F1, which is the final demand from the network for fuel, determines how much is the fuel that will be going out, and F2 is the final demand that determines how much electricity is going out. When we say that the goal is to quantify the life cycle environmental impact of producing 500 kilowatt hour of electricity, we are setting F2 to be 500 and F1 to be 0, because we are not interested in the fuel production going out of the network. So, when we see the goal, the first thing we can do is we can write that for this system or for our goal, our F1 is going to be 0 and our F2 is going to be 500 kilowatt hour. So, now we have set up the first variable in our mathematical problem. The next thing is we can write our balances like we did in the last module and set up the technology matrix. To do that, we have two products in the system, the fuel and electricity. So, we write the balance for fuel and then for electricity. So, if you have to write the balance for fuel, the production of fuel is 100 times S1 and the consumption of your fuel is 20 times S2, where S1 is the scaling factor. So, S1 is the scaling factor and S2 is the scaling factor for process 2, and that net will give F1, which means that this is the net amount being produced in the network, this is being consumed in the network, and whatever is left over will be going out of the network. Of course, here we are setting F1 equal to 0, which means that we only want to study the impact of producing fuel for electricity production. Similarly, we can write for electricity, in the whole network, the only thing that is happening with electricity is the production. So, we have 100 times S2 is equal to F2. So, if you remember, this will help us get our technology matrix 100 minus 20 and 0 100. This is our A, which is the technology matrix. Now, our problem is defined. We can set F1 to be 0 and F2 equal to 500, and you can use AS equal to F or S equal to A inverse F to calculate your scaling factors. So, when you do that calculations, your S1 and your S2, so your S2 will come out to be 5 and your S1 will come out to be 1. So, now we know how much we need to scale each of these processes to meet the impact of producing 500 kilowatt hour of electricity. You can see that production of electricity, of course, because there is no consumption in the network. So, we are scaling it linearly to just get the whatever our goal was, and there is no output or the demand of fuel outside the network. So, the scaling is only to meet the demand of your fuel in the network. So, since when you scale your second process by 5 times, you would need 100 liters of fuel. So, we do not need to scale it further, just scaling S1 equal to 1 will satisfy that demand. So, now we need to calculate the environmental impact, and for that we can set up our intervention matrix which captures the environmental impact. Remember, to calculate environmental impact we include both the resource consumption and also the emissions. So, we can do that. So, for the environmental impact, we can write our equations as R crude. So, crude oil consumption will be minus 300 times S1, R CO2 is mainly we have 60 kgs in times S1 from the first process and 20 times S2 from the second process, and our SO2 is 12 times S1 plus 1 times S2. So, straightforward equation, we have seen that we can write it in matrix form. So, this is our intervention matrix B and then the scaling factor, and that is the R, which is the vector that contains information about total resource consumption and emissions production. So, when you plug that value, your values will come to be, so we already know our scaling factor is S1 equal to 1 and S2 is equal to 5. So, when you do that calculation, that will come out to be 300 liters of crude oil being consumed, 160 kg of CO2 being emitted from the network, and 17 kg of SO2 being emitted. So, this was a straightforward simple application of the process network algebra to calculate the total environmental impact based on the goal defined for your LCA. You may think that this is a very trivial calculations, of course, because we only have a very small system of 2 nodes. If you have a large network of, let us say, 10 different processes that you are including in your LCA, then this will become a intricate or a very tedious calculation. Therefore, the matrix network algebra is really helpful because you can set up your intervention matrix and you can also set up your technology matrix based on your system. Then whatever life cycle you want to perform, you can change the final demand vector and use MATLAB or any other programming software to calculate the life cycle environmental impact. So, network algebra definitely eases the process of doing this calculation, and we can also see where the impact is coming from by going through the network analysis itself. So, let us move forward. Our next complication in the network algebra or the next enhancement in the network algebra comes when we are considering system that has multiple products. So, the example that we just looked at only had one product from each process. So, my fuel production process was making fuel and my electricity production process was making electricity. In reality, however, you can have systems that can make multiple products. So, your fuel system can be making a byproduct that could be displacing some other product. Similarly, your electricity production can be making a byproduct of heat that replaces heat requirement from the cogeneration plants. So, this will cause the issue of allocation. We have covered the topic of allocation and the complexities of dealing with allocation in LCA systems and recycling system in the previous module. Here we will see simple example of applying the process network algebra in case of first avoiding allocation, where we would be using the displacement, and then the partitioning, which is a simple way forward to use allocation if we do not have detailed information to use displacement. Of course, we will see that applying both of these approaches will require us to modify the original life cycle network by introducing a new unit process. So, let us go over this process network algebra. I would like to highlight the details of lot of these methods are also in the textbook Sustainable Engineering that has been mentioned as part of the pre-required textbook for this modules. So, let us look at the problem. So, here now we have the same process, we have fuel production and electricity production, but now we have modified our unit process for fuel production with a byproduct that is also being produced along with the fuel production. So, of course, what that means is that all the impact that is coming from the fuel production cannot be actually assigned to fuel production, because there is some byproduct. Of course, if this byproduct is a complete waste, it does not have an economic value, then we can say that all the impact is for the fuel production itself. But if the byproduct has an economic value and it gets utilized, then we cannot say, we should not be assigning all the impact of process 1 to the fuel. Also, these days lot of the waste production products are going into secondary life or into the recycling system. In those cases as well, we will need to consider what is the impact that we need to give to the byproduct along with the fuel production. So, here let us look at how we do partitioning. So, partitioning is when we are not avoiding allocation, we are going to allocate the impact of fuel production process to both fuel and byproduct. So, when we are doing partitioning, what we are assuming is that there are two separate sub processes that are making the fuel and the byproduct within that process. Of course, if you have the stoichiometry information, you can accurately allocate the crude oil, electricity, SO2 and CO2 to either fuel or byproduct. In case you do not have such detailed information, we can use the partitioning system. So, let us see what we do. So, to do that, we now divide the fuel production system into two sub processes. So, you have now a fuel production process 1, P1A, and fuel production process B, and you can see that what we have done is that we have partitioned the fuel production process into two different processes. Each of them are only making one product, either fuel or byproduct. Of course, this is not always possible, so this is kind of an assumption, and then we will be giving weightings to each of the resource consumption depending on the volume being produced. So, here since we have 20 liters of fuel being produced and 10 liters of byproduct, so we will give the weighting to this process A as 20 by 30. Okay. So, the amount of crude oil that will be input to this system fuel will be 50 times W1A, and the crude oil that is going to the fuel production B or P1B, which is making the byproduct, will be W1B, which is the weighting to the second sub process, and that is about 10 by 30. Again, so this will be 50 times W1B is the amount of crude oil that we are assigning to the fuel production process that is making byproduct. Similarly, we will say electricity is 2 times W1A as the input to the fuel production A, which is P1A, and electricity is 2 times W1B, which is the fuel production process B. Now, similar thing we can do for the emissions as well. I have not shown it, but we can also say that your SO2 will be 2 times W1A and your CO2 will be 10 times W1A, and here the emissions, your SO2 will be 1 times W1B and CO2 will be 5 times W1B. Okay. Now, we have split the process. With this, what we have done is we have expanded our life cycle network from a 2 process network to a 3 process network. Now, when you do the calculations, what you would do is you would modify your matrix algebra to represent these processes as separate. Again, we follow the same approach of writing the equation balance for each of the product. Now, instead of 2 products in the network with F1 and F2, we also have a third product. So, we will follow the same approach. We will write equation for each of the commodities and develop our new technology matrix or the enhanced technology matrix. So, let us look at the matrix. So, first we have our calculation or the balance for the fuel system. So, we have we have our fuel as 20 times, this is being produced in the system, and we will have S1A, which is the scaling factor for the process 1A, and S1B, which is the scaling factor for process B. So, for the fuel it will be 20 times S1A minus whatever is being consumed, 5 times S2, and then that is the whole thing that is being consumed. So, for fuel the balance is 20 times S1A minus 5 times S2, which is the process 2, is giving the fuel. So, this is the balance for fuel production in the network. Then we will look at the electricity. So, electricity is being produced as 10 times S2, and then it is being consumed in both process 1A and 1B. So, let us write the consumption of electricity is 2 times W1A. So, this will be minus 2 times W1A times the scaling factor, similarly minus 2 times W1B scaling factor for B, plus it is being produced in electricity 10 times S2, and that is equal to F2, which is the net electricity production in the network. And now, since we have modified our system to get a third product as byproduct, so we will write a balance for byproduct as well. So, we have 10 times being produced and we do not have anything being consumed. So, we can write that equation as 10 times S1B is equal to F3. So, now let us look at the modified technology matrix. We have 20, 0, minus 5, we have minus 2 times W1A, minus 2 times W1B and 10, and this is going to be 0 and 0 and 10. So, here we have our S1A, I think we have to write, this is going to be 0, 10, 0. We have S1B and then S2. So, the first one is 20 times S1A, 0 times S1B minus 5 S2. The second was minus 2 W1 S1A minus 2 W1B S1B 10 times S2. The third one is 0 S1B 10 times S1B and 0 times S2. So, here times S1B, this is equal to, the first one is F1, the second one is written for F2 and the third one is for F3. Okay. So, that is our new equation, and now when you have to, so this is our modified technology matrix and this is our modified scaling factors. So, now when you have to set up a new study where you want to study the impact of fuel, then your F2 will be, which is the demand, or of F3, which is the demand for byproduct, can be set to 0, and we can see the actual impact of just the production of fuel, because we are eliminating the burden that is being done because of the production of byproduct. So, now we can see. So, here let us look at our original technology matrix. So, your original technology matrix will be just 20 times 20 minus 5 minus 2, 10, and so your So, you can see that our original did not have the third column. So, we generate that third column by adding in this, splitting this particular input into 2, where we have the weighting factors. and we have instead 3 different scaling factors now. Whenever you are looking at these systems, you would want to see wherever you have multiple co-products, you would be partitioning that particular process into 2 process or maybe 3 process depending on how many co-products those have, and then writing the specific balance for each of the byproduct and the main product for that particular matrix. So, that is the way we develop what we call as the partitioning or partitioned technology matrix. Now, the system is all set up, we can use based on the goal of our LCA if we are including this system by setting the right final demand in this system. Okay, so let us move forward and we will look into the other case. In the other case, we have the framework for displacement. Here we have a different idea. The idea is that we prefer not doing allocation. Here again we have the byproduct being formed, but what we do is that we identify an alternate route for making of the byproduct. In this case, let us say our byproduct has an alternate route of production called as byproduct production, which is instead of taking crude oil is based on the biomass input, and this process, as you can see, has a very different impact. So, the idea with displacement is that whatever byproduct is being produced by this fuel production process, because it is making fuel, it is also fulfilling the demand of byproduct that has to be separately produced, which means that this will have a negative impact on this process. So, we can put that as negative output. So, the way we do the displacement is that we introduce the system and we make the output from this system as negative, because we are saying that whatever is being made by process 1 is displacing this production process. So, we include this unit process and we suppress that output from that unit process, and we will see how we do it in the matrix form. So, let us see, again we will write 3, now again we have a 3 different processes. Here instead of splitting this process, we are representing the byproduct formation by a different route for byproduct production. So, here what we will do is we will write a different matrix. So, again we have the same output or the same formation for the process 1 and process 2. So, 20 times S1 minus 5 times S2 is equal to F1. Your fuel production balance does not change. So, that is saying that I am going to scale this by S1, this is going to be S2, and now this process is going to be S3, because this is not split off of the first process, we are introducing a alternate route or new unit process in our network diagram. So, now we have the fuel production systems remains the same. For the byproduct or for the electricity, we can write 10 times S. So, 10 times S2 minus 2 times S1. So, 10 times S2 minus 2 times S1 is equal to F2, where F2 is our electricity production from the network. And then the last we will write a balance for the byproduct. So, in this case the byproduct that is being made is 10 times S1 and we want to reduce the output from this one. So, we are going to say minus 2 times S3, which is going to, so we can write that we are going to increase the production of byproduct by 10 times S1, but we are going to reduce the production from the alternate route. So, we are going to scale it further and that is F3. So, that is going to be the byproduct production in the network. The idea is that we cannot avoid the formation of byproduct in process 1. So, 10 times S1 is definitely going to be made in the network, but then we have an idea of displacing the other process. So, we are going to reduce the production from the second one, saying that because it is going to make 2 times. So, if I scale it by 2 times S3, we are going to reduce that output. When we are going to reduce that output, it will ultimately reduce the biomass requirement and CO2 from this system. Hence, the displacement idea in the LCA is telling that because of that byproduct formation, we are reducing the impact somewhere else. Therefore, this process gets the credit for formation of byproduct. So, now the modified technology matrix is simple. We have 20, minus 5 and 0. Then we have minus 2, 10, 0. We have 10, 0 and minus 2, and we can write it as S1, S2 and S3. So, you can check for the matrix calculation or the multiplication. So, again, because we had a byproduct, we expanded our network to include a unit process. So, instead of solving a 2 by 2 matrix, now we are going to solve a 3 by 3 matrix. The rest of the approach in establishing these methods are same. You can do the same thing for calculation of your intervention matrix. So, here now since we have S1, S2, S3 from this system, once we have set up our F1, F2, F3, we can calculate this and then eventually calculate the R for each of the system. For the displacement process, we are going to reduce the values, because remember we are saying that the output has been reduced. So, displacement, we are going to reduce the emissions and the resource consumption. So, when you work out the math, eventually you will know how much you want to reduce. So, you will know the R biomass. Here the consumption is going to be minus 10 times whatever S3, and we are going to reduce by that amount, and R CO2 is also going to be minus 5 times the S3, whatever we are getting the S3 for reduction because of the net production in the network, that is what we will get. Okay. So, those are the two different enhancement to the process network algebra that we see when we are doing allocation, when we need to account for the production of co-products in a unit process. The first one is partitioning, where we split the process into two additional unit process. So, then you write the balances accordingly and you set up a new final demand vector. And when you are doing displacement, you add an alternate unit process where you are again introducing it and then behaving the network as reducing the demand from that displaced process. So, it might sound confusing, but when you do the math, it comes out very straightforward. Once you have set up those two new additional matrices, the idea is that we set up the final demand vector based on the goal of LCA study, and then we calculate the total environmental impact using the intervention matrix as we have seen in the simple case of process network algebra. So, now we will look at into some example for it. Let us look at a simple example. In this example, we have the same case of byproduct formation in fuel production process, and we have the electricity production process. The goal of our LCA is to calculate the impact of producing 100 kilowatt hour of electricity and 100 liter of fuels from this life cycle network. Of course, we are not going to produce any byproduct, but we cannot avoid production. So, we need to allocate the impact to only fuel. So, we need to partition the impact that is going to the byproduct. So, here we will be establishing the network using the partitioning. So, we will calculate the W1A, which is the weight given to the fuel production A, and W1B, which is the fuel weight given to the P1B. So, W1B is 10 by 30 because 10 liters of byproduct and total product is 30, and W1A is going to be 20 by 30. And so, your crude oil will go into for 50 times 20 by 30 for this one, and this will be 50 times 10 by 30. Similarly, for electricity, it will be 2 times 20 by 30 here, and this will be 2 times 10 by 30. Okay. So, now we have calculated that. Similarly, we will do SO2 and CO2 as well, but let us look at the scaling factor calculation. So, simply we write the balance. So, 20 S1A minus 5 S2 is equal to F1, that is the fuel production. Then we have minus 2 1A minus 2 1B and plus 10 S2 is equal to F2, that is the electricity production. So, your F1 is the fuel production from the fuel demand from the network, your F2 is electricity demand, and your F3 is the byproduct. From the goal of the LCA, we know, so let me first write the third one, which is 10 times S1B is going to be F3. So, if you go back, the goal of our LCA is to, the goal is to produce 100 kilowatt of our electricity and 100 liter of fuels. So, my F1 is 100 liter of fuel and my F2 is 100 kilowatt hour of electricity. So, now we can go here and we can say that my F1 is going to be 100, my F2 is going to be 102. So, this is liter, this is kilowatt hour, and your F3 is going to be 0 because we are not interested in making byproduct. So, now when you do this calculation with setting your F1 and F2 and F3, what you will do, you will get is, let me write it in the matrix form. And when you solve this, you will get S1B is equal to 0, your S1A will come out to be approximately 8 and your S2 will be coming out to be approximately 12. So, now we have the 3 scaling factor that we need, and you can see that S1B equal to 0 because it makes intuitive sense as well, because we are not interested in making byproduct as a final product. So, since this is the process that is making the final product and we do not need byproduct as any input to the processes that are involved in our life cycle. So, we can say that the scaling factor for this should be 0, we are not interested in any production from that. So, what is effectively happening is we are taking the partial resource consumption and emissions as what is going to the, what is attributed to the fuel production. The rest is actually wasted because we are not interested in that byproduct as a product. So, we can calculate with this, we can calculate our RCO2 as 10 times W1A S1A plus 5 times S2, and our W1A, I just want to remind, was 20 by 30 and W1B was 10 by 30. Okay. And when you calculate that, value will come out to be 113 kg of CO2, and we can also calculate RSO2, that value is 2 times W1A S1A. So, 2 times W1A is taking care of the portion of that SO2 emission from process 1 that is attributed to the fuel production, and S1A is the scaling factor that we need for the amount of fuel production that we need to produce from our goal, and then 1 times S2, and that value will come out to be 22.67 kg SO2. So, these are some simple demonstrations of how your results will change or how you will do partition, or how you have, if you have a simple system, how you set up your matrix algebra, and if you have a displacement, it will follow the same approach. It is just that you need a new unit process information. In summary, in case of multiple co-products, the suggested method by ISO is to avoid allocation by using displacement. It is always better to think of that we are going to displace the production, because now we have these additional byproduct being made in this life cycle that can be also sold in the market. So, it competes with the other process. So, you are reducing the environmental impact by selling it in the market, because now the displaced process needs to make less. In case there are no alternate routes available for that byproduct, then we are going to say that it is not actually competing, but it might be that it is using that partial amount of resource, and we have to just partition the impact of that process into the main product and the byproducts. For LCA calculation, we will use the modified technology matrix and the modified intervention matrix with appropriate final demand. The matrix algebra actually for a small system is not really important, but when you start doing LCAs at the large scale where you have hundreds of processes in your LCA boundary, then this matrix algebra is really helpful. So, now you are equipped with the foundational matrix formulation that you can set up your own LCA calculation in any software of your choice, be it Python or MATLAB. So, thank you for coming to this module, and we will look forward into the next steps of LCA in the next modules.